I'm telling you, this might be one of my lowest effort weeks that I've ever had in streaming, but riding off of the back of debilitating illness, I really don't blame myself, honestly. And if not lowest effort, maybe highest scuff, because, man, today is the first time where I'm actually just going to be, like, finishing my dinner on stream. I took my sweet-ass time, getting ready for stream today, and let me turn down the music a little bit as I chat. There we go. I took my sweet-ass time getting washed up and everything after work today, and decided tonight I wanted to have some baked potatoes, and by baked I mean microwave potatoes, and I dressed it up and everything, and it's great, but it is like, it took me maybe too long to get my act together, so I'm now going to be eating like 2/3 of a potato on stream while talking about hazardous chemicals. At the very least, I'm not eating chemicals while I'm in the lab, so I'm not, like, violating any safety rules, but yeah, it's, it's hitting. I'm tired as well today because, like, yesterday I was playing Baldur's Gate 3 as usual for Baldur's Gate Wednesdays. Me and my friend DirtNolk are wrapping up our Baldur's Gate playthrough. We're almost done. In fact, we're so almost done that I had to make him stop in the middle of the final boss fight because I needed to go to bed, and I was still staying up a little bit too late for my well-being and health. I mean, nothing egregious, but I could have really used another 30 minutes of sleep. It would have made all the difference in the world today. So, yeah, it's a scuffed week and a scuffed stream, everybody. But thankfully, I mean, it's not like it's that hard to do a React stream, and chemistry is my element. Get it? So like, I'm pretty cool to just end up yapping about some chemistry stuff for a while, and let the video play and all that. So, yeah, let's get to it. Pause the Mega Man. Well, hold on. We'll first switch the screens. Right. All right. There we go. Okay. I'm still transmitting. Yeah, I'm still transmitting. Everything's good sound-wise. Alright. Almost pause the Mega Man X8 music, because today I'll explain, I guess, what we're starting off with today. This is what in my opinion, like, the bread and butter of chemistry YouTube videos. This is what is, like, in a weird way, it's almost equivalent to the Let's Play of chemistry YouTube, where it's just, like, this is somebody making something in a certain specific way, may or may not be novel pathway, and it's just the pure act of making a molecule and purifying it and isolating it. It is as chemistry as you can get, just mixing shit together and figuring out how to get the shit that you actually want out at the end. Today's first feature is going to be from Apoptosis, which is a video titled Making Benzaldehyde from Paint Stripper, which is really quite, really not really that much of a feat, but at least chemically speaking, but it is still, interesting enough to be worth watching, in my opinion. So for, I guess, first context is the molecule I currently have drawn here on the side. That is benzaldehyde. It is, as the video is going to, I think, explain here in the very beginning, the name comes from this being a benzene ring, this 6 carbons, 6 hydrogens in the center, all in a circle, and the aldehyde group, the most simple aldehyde group possible, and the aldehyde group being defined by a carbon with a double bond to oxygen, and then next to that, oh, actually, wait, sorry, that should not be H3C. That's not what benzaldehyde looks like. Delete that. No? Oh, I'm on the wrong layer, that's why. I accidentally drew benzaldehyde with one more methyl group, and it would no longer be benzaldehyde. It would be like benzyl ketone. I think the most simple benzyl ketone. Benzyl acetone. Benzyl acetate? Nah, it's not that, but it's something similar. There we go. That's an aldehyde. An aldehyde is defined by the simple group of hydrogen bonded to a carbon, which is this vertex here in the middle, double bonded to a oxygen, and then the carbon is lastly bonded to something else, which is the benzene group. This is one of the simplest aldehydes you can have. It is the simplest aromatic aldehyde, as it's known, because benzene is known to be an aromatic group due to the way its electrons are organized. A little bit outside of the scope of the introduction, so I'm not going to go through that, but this is benzaldehyde. It is, as kind of noted here in the title screen, it's a cherry flavoring agent. It's your artificial cherry flavor and smell. It'll be very familiar to you. It's also useful in different types of synthesis reactions because it's fairly easy to have various molecules want to actually attack this carbon center here. It's electron deficient. So if you provide something that is rich in electrons, like say you provide some kind of amine group, so if I draw like a really simple amine, let's say something like this. Yeah, this kind of amine with a carbon chain leading to it. It's nitrogen, has electrons. It wants to go in, bond to this carbon, displace the oxygen, and through multiple steps, it would create an imine group with then this part hanging off of it. And this is very useful for like pharmacosynthesis. That's not the word. Hold on. I need to get the syllables right out of my mouth. Synthesis of pharmaceuticals for the most part, as well as other random organic syntheses. So this compound has synthetic use as well as being a food additive. Now the part where it's going to be how do we get this from paint stripper is actually probably a lot simpler than you might be thinking. So for those, oops, wrong layer, click that right, there we go, okay. For those who don't know, one form of commercial paint stripper that's very common, especially now that if you're in the United States, dichloromethane is no longer a easily obtainable chemical, is toluene. Toluene has this this structure, if I can draw it. CH3. So yeah, this would be toluene over here. And in order to go from toluene to benzaldehyde, you could probably see that, all right, what you need to do is just remove the two of the hydrogens from this carbon at the top and put an oxygen on there. You know, of course, it's easy to say these things. It might be a different story to synthesize it, but it should actually be a fairly simple synthesis, all things considered, because there's, for reasons that I both don't quite remember, but for reasons I both don't quite remember or entirely understand, the carbon that is near a aromatic ring, a benzene ring like this, is pretty easy to oxidize, at least compared to a carbon that's just in the middle of a straight chain of alkane like that. So this is basically just going to be adding an oxidizing agent to toluene, seeing if you can't get the aldehyde group to form on the end, and boom, there you go, cherry flavor. So now that I've gotten the explainer out of the way, we can pause the music and actually get on with the video. Let me do just that. Although I do love listening to Noah's Park from Mega Man X8 quite a bit. I kind of want to replay Mega Man X8 now. Next opportunity. Maybe I'll hop in the voice chat in Discord over the weekend and do some of that. I still need to finish the hard mode, so I may as well, right? Alrighty then.
Today I'm going to make some of this ordinary paint stripper into a super useful chemical called benzaldehyde. If you've never heard of benzaldehyde, it's basically just a benzene ring containing a single formyl group, making it the simplest possible aromatic aldehyde. It smells a lot like cherries, and despite being basically composed of incredibly carcinogenic benzene and formaldehyde, benzaldehyde itself is fairly non-toxic and widely used as a flavorant in cherry sodas. Benzaldehyde is also widely used in organic synthesis, where it undergoes aldol condensations to form cinnamaldehyde or styrene derivatives. It can also condense with itself to form benzoin or...
That's a fair point. Different synthetic possible pathways. I won't linger too much on it because I don't think it's going to be the point of the video, but an aldol condensation is another fairly typical synthetic pathway, although it tends to be a bit of a messy one just because the energetics of the reaction are not that much in your favor. They kind of push forward, but not very effectively. So, let's see. Effectively, what an aldol reaction is when you have... How do I... I'm trying to remember how to do this, actually. Aldol reaction has to do with merging two different ketones together. Because these hydrogens on the ends here of a given ketone group are, relatively speaking, acidic. Not that much, but you put it under sodium hydroxide at high heat, it will disconnect one of the hydrogens. Oh, hold on. Uh-oh, wrong button. Right. I get confused between redo and undo in certain programs. Yeah, if you have a strong enough base and blast it with heat for enough time, you can remove one of these hydrogens, put a negative charge here. The negative charge is stabilized by moving electrons back and forth with the nearby carbon-oxygen group. And then by virtue of there being another aldehyde, usually the same molecule, or sorry, not an aldehyde. Well, it could be an aldehyde. Another ketone group, so another carbon-oxygen group to attack. As I just mentioned before, they're pretty vulnerable to electron-rich groups, so one molecule that just got its proton stolen will then go to the next molecule and attack that, and now a carbon-carbon bond is formed, and through a couple extra steps, this oxygen gets kicked off as water, and you now have formed a carbon-carbon bond, which is the fundamental structure to all of organic chemistry. So you're doing something that is not terribly easy to do and pretty permanent once you actually do it. So aldol condensations are very useful for actually making larger molecules, or larger carbon-based molecules. So yeah, it's fairly important for that kind of synthesis as well.
Or with dimethylaniline to form malachite green dye. Cyanide will react with benzaldehyde to produce mandelic acid, while nitroalkanes will react with benzaldehyde to produce phenyl nitroalkenes. These are all incredibly important reagents in further synthesis.
All groups that I will not be spending time drawing all of them.
A wide array of useful dyes and pharmaceuticals. I plan to make videos on several of these in the coming weeks and months, but before I could do that, I needed to make the benzaldehyde itself. This is something I'd wanted to do for a really long time, but I kept putting it off since virtually every method I came across seemed to require either excessively difficult to get starting materials or produce comically low yields. At a certain point, I figured I'd settle on the classic Attard reaction.
I'm gonna read what he has here. Let's see. Benzaldehyde future project, low phen, methods considered for the synthesis from benzoyl chloride, oxidation of benzyl alcohol with dilute nitric acid. Probably the easiest method, done too many times already. All right, yeah, I guess you gotta remember this guy's also a YouTuber too. So if you do the same, it's kind of like doing any. the Let's Play analogy is actually better than I thought, because it is kind of like any Let's Play on YouTube. You can do one, and you can do it the same as everybody else has. You can right now go boot up Mega Man X and play it, but unless you're bringing something new and different to the table, it's just going to be another Mega Man X playthrough. It'll get lost in the sea of reactions. It's like if he did the typical reaction, probably wouldn't get much traction. Bars. So now I just have to think of something a little bit more creative to do, which, honestly, I always, I will always be interested in people going for accessible hardware chemicals as their starting materials, so God bless you for going for toluene first.
As it seemed to be the best option with what I had available to me. However, this method had two major problems. Number one is that the Attard reaction uses the incredibly toxic, volatile carcinogen chromal chloride as an oxidizer.
Yeah, Christ, chromal chloride. That is one of those chemicals whose names is would automatically give any person who values their health and safety within chemistry an immediate red flag. Chromal chloride has a structure looks like this. It's very dangerous because this is chromium in what's known as the +6 oxidation state, written kind of as chromium Roman numeral 6. And this is bad exclusively for your body. It is carcinogenic. It's extremely toxic. It is also environmentally polluting. And I believe it's so toxic because it is very electron poor. It wants to pick up things from your body that want to bind to it, like all those amine examples that amine example that I gave at the very beginning, condensing with benzaldehyde. And I guess in a kind of rare scenario, I think the body has a couple of enzymes that rely on chromium's heavier cousin on the periodic table, molybdenum. And given that molybdenum and chromium have very different sizes, atomic sizes, there's a non-zero chance that chromium could replace molybdenum in an enzyme if you have enough in you. And that, given the size difference and the electronics difference between the two elements, there's a good chance that whatever enzyme was fueled by the molybdenum center is completely and utterly shut down by the chromium, replacing it at the center. It just does, the protein doesn't unfold correctly anymore, and it just does some kind of either non-function or actively bad function. So, yeah, no, chromium-6, very bad for you. The Itard reaction is one of those that was certainly developed before health and safety was a consideration in the chemical field. So, I mean, I actually don't know how old it is. Probably, I think this is one of those, like, that's from, like, the 1800s. It's so old, like, late 1800s. Oh, God, and the reaction also calls for carbon tetrachloride, too, which, yeah, that is a carcinogen and a half. Carbon tetrachloride, very notable for being useful in liver cancer studies, because you give this in a small dose to a mouse, they will contract liver cancer 100% of the time. It is a very, very consistent carcinogen, and there's a good reason why this was phased out of all industrial applications globally in the 80s. Remember when we could actually have environmental progress as a society? As not just a society, but as a global society? Those are great times, weren't they? Anyhow, back to benzaldehyde.
Which I wanted to avoid if at all possible. Number 2 is that despite me thinking this was a classic organic synthesis, I really couldn't find any concrete procedures or videos online of this being done. I was
just
within
no one
a
wants
few
to work
hours
with that
of
shit.
Just winging it as usual, but then I was informed that Nile Red had actually done the Itard reaction before in a somewhat recent video to make some DIY cherry soda.
Oh, yeah.
I figured I'd at least give it a quick look to see what kind of misery was in store for me, and after seeing the massive volume of liquid carcinogen...
Yeah, which also leave it to Nile Red to make his cherry flavor using the most carcinogenic method possible.
That I'd need to produce in order to make a tiny volume of benzaldehyde, I decided to go back to the drawing board. Later that same day, almost by chance, I came across an old patent on converting alkyl-substituted aromatics to their respective aldehydes or ketones using persulfate salts as an oxidizer. I was pretty skeptical at first, given that persulfate seemed like an extremely strong oxidizer for making such a delicate molecule. But when I saw the reported yield of 95%, I decided I had to give it a try. To get started, I began by adding a half gram of ferrous sulfate heptahydrate.
Interesting. So what are these reagents? Okay. Methanol, I'm guessing, is going to be just your solvent, so that's not going to be too important. Although maybe it could be contributing to the reaction a little bit. Need a polar solvent for good oxidation, maybe. Sodium persulfate, I know, has oxidizing properties from my personal experience with the oxidizer oxone, which is good for converting alcohols to ketones, if you have the right solvent. that's a different chip off my shoulder. Let's see. Some copper 2 acetate, which I'm guessing is the thing labeled verdigris, and then some iron 2 sulfate heptahydrate. Okay. Huh. This is interesting. This gets into a area of inorganic chemistry that I'm not as familiar with, because this definitely does just seem like throwing a bunch of salts in a vat and hoping that they actually react with the product that you, or with the target you want it to react with. I'm guessing there's going to be some kind of redox action with the persulfate ion, because that's a fairly oxidized ion that can maybe do some interactions with the metal. I don't know. Hopefully he actually has a reaction mechanism for this. Although, given that it was from a United States patent from however long ago, I kind of doubt that that is important or included.
And 1 gram of copper acetate to a 2-neck round bottom boiling flask.
Trust the science, bro. Trust the
milliliters of a 20% ethanol solution. The iron sulfate is going to be the key oxidation catalyst here and can be substituted with other iron salts or silver nitrate. The copper acetate, on the other hand, is technically not required, but it is highly recommended as it works effectively to inhibit various side reactions, particularly the dimerization of the benzaldehyde to benzoin. The ethanol is also technically optional, but used to help increase contact between the organic and aqueous layers during the reaction.
I wonder why the copper would prevent dimerization of this benzaldehyde molecule. I mean, copper is fairly oxophilic. It would be fairly prone to some... oh, wait, hold on. That's the wrong layer. It wouldn't be unreasonable for copper to maybe kind of, like, be bound to by the oxygen, and it would kind of stick it around, maybe withdraw some electron density from the group, but that would make that group more active. So if there was another group like this around, theoretically we could kind of get some, I don't know, attack, reduction action. Huh. Now that's interesting. I really don't know why that would work. Unless maybe one thing I could think of is that I have seen in the literature some reactions where copper is used as like an oxygen scavenger. So in a sense that if maybe the dimerization of this needs oxygen from the air, which would be in the flask, to kind of kickstart it, needs that extra oxidizer, the copper itself would be good at scouring for that oxygen in the air and then reversibly kind of diverting the electrons away. It's a mechanism I can't quite think of off the top of my head, but I know it is something that does exist in the literature and is used in industrial applications often, so maybe that's it, but that's just me speculating entirely.
Anyway, after allowing this to mix for a few seconds, I next added 50 grams of toluene paint stripper and allowed this all to continue mixing for a few minutes. Meanwhile, I next dissolved 280 grams of sodium persulfate in a minimal volume of water, and this represents...
Then it says to dissolve the persulfate in a methanol water mixture. When I tried this persulfate, violently oxidized the methanol to formaldehyde when gently heated. Yeah, I guess that makes sense. If your goal is to oxidize a carbon group or a CH3 all the way up to an aldehyde, then yeah, there's no good reason why it wouldn't just oxidize your methanol. But I don't know. Maybe shit was different. Just shit was different and tainted back then. Maybe they could get away with the methanol water mix somehow. Huh. Yeah, easy way to make formaldehyde. That's not something you want to be able to do. That's just a way to poison yourself really fast.
It's a little more than twice the molar equivalent of the toluene. This might seem like a lot, but this huge mass of salt is necessary to fully oxidize the toluene to benzaldehyde. Once the sodium persulfate was done dissolving, I set the boiling flask up with an addition funnel and a thermometer. The thermometer was set to monitor the reaction temperature, and the addition funnel was filled with the saturated sodium persulfate mixture. I next transferred all of this to a heating mantle, heated the mixture to around 75 degrees Celsius, and then slowly opened the stopcock to add the sodium persulfate to the reaction mixture dropwise. Now, because I'm trying to get water-soluble sodium persulfate to react with water-insoluble toluene, extremely aggressive stirring is absolutely necessary here.
Think of it like a vinaigrette.
And I quickly realized that the weak stirring function on my heating mantle was simply not going to cut it. To try and fix this, I decided to quickly cut the heat and move the boiling flask to my hot plate to continue the reaction. The stirring on my hot plate is way stronger than my heating mantle, and at this point, you really don't need to apply that much heat anyway.
As I say, good to point out the reason that he's probably adding the persulfate solution slowly is because oxidation reactions, like the one from toluene to benzaldehyde over here, tend to produce a lot of heat, and especially when you have a reaction that already needs heat to kind of get it jump-started, you could very quickly end up with a absolute runaway disaster of, like, the reaction needs heat, but then it produces heat when it's actually done oxidizing, which then causes, you know, another molecule to react even faster, and then another molecule reacts faster, and so on, so on. And you just get a runaway reaction where there's so much heat in the flask, your methanol solvent's going to start to boil, or you get unwanted side products. And yeah, in that worst case scenario of like it boiling over, it's just like your your liquid and product just go everywhere and cause burns, and it's bad. You don't want to let your temperature get away from you.
That end, at this point all I really needed to do was continue to slowly add the sodium persulfate mixture dropwise under very strong stirring while maintaining a temperature between 65 and 80 degrees Celsius. This ended up taking quite a while given the massive volume of persulfate, so while this is playing out, I'll do my best to try and explain what's going on here. If you take a look at our starting reagent toluene, you can see that the molecule is basically just benzene with a single methyl substituent.
Yep,
the
got that
hydrogens
covered.
bound to this methyl side chain are particularly reactive, and this is due to the stability of the benzylic radical ion formed after the hydrogen atom is abstracted.
No, that actually totally makes sense. So, I guess to explain, what he's kind of talking about a little more, if you, oopsie, that deleted a layer. If you have your toluene molecule, which I have to draw slowly every time. I wish I just had a hexagon feature on my drawing kit here, but maybe one day I'll get smart enough to actually, instead of streaming in paint.net, I'll stream in like ChemDraw or something professional to use. But yes, if you have your toluene and you end up having ripping off of a hydrogen, whatever charge or lone electron ends up on this carbon. So say like in the diagram over there, you take off a hydrogen radical, and you just end up being left with, hold on. Let me change colors maybe to emphasize this. So let's see. Take off a hydrogen radical that goes to somewhere. End up having this one lone electron here on the space. This lone electron can steal some electron density from this double bond, which then kind of moves the radical over here. But then that could steal from this one over here and pair up there. And then you basically end up having the situation where this one lone electron, or if this was instead of lone electron, just the hydrogen got pulled away and the two electrons in this bond were left over, you have a place for these lone electrons to go and just circulate throughout the ring. And an electron with more space to wander through is a more stable electron. Because just due to quantum physics, small particles like electrons really don't want to be confined to a small area of space. So if you give it a larger area of space, then it'll be more willing to be left behind in a reaction like this. Alternatively, if this ends up being the opposite and both of these electrons go away with whatever reaction happens and you're left with a plus charge behind, then you have a double bond that could fill in the plus charge a little bit, help distribute that emptiness a little bit more as well. So, yeah, you end up having that being a fairly reactive methyl group.
And this is because the intermediate is resonance stabilized by the pi system of the adjacent aromatic ring. As a result, the carbon of toluene's methyl group is more susceptible to oxidation than the aromatic carbons. Now, I haven't been able to find any mechanism for this reaction, but I assume it begins with a nucleophilic attack by the methyl carbon on the peroxide oxygen of the peroxodisulfate ion to give an intermediate sulfate group. This sulfate group would then be quickly hydrolyzed to a hydroxyl group formed.
Okay, what the hell is he saying here? Back up for a second.
but I assume it begins with a nucleophilic attack by the methyl carbon on the peroxide oxygen.
By the methyl carbon on the peroxide oxygen. Here you're showing the Ebbs sulfite sulfate oxidation, which is a completely different reaction, but I imagine the hydrolysis and rearrangement are the same. Okay, that makes things a little bit confusing. So let's see, he's saying what?
And the nucleophilic attack by the methyl carbon on the peroxide oxygen of the peroxodisulfate ion to give an intermediate sulfate group.
Uh-huh. Interesting. Okay, I'm going to draw this to maybe try to follow along here. So he's saying, hypothetically, just kind of spinning an idea. Start with the toluene group here. I'm just going to abbreviate the ring as a circle. It's a typical typical practice. So he's saying that within the the persulfate group, you end up having the, let's see, O4. Okay, yeah, I can abbreviate this fairly easily, I think. Something like O3S oxygen SO3. Each of these has a 1- charge on either end. He's saying that starts off with a free radical attack on the, that should be a double bond or a single arrow. It's hard to draw that. There we go. The peroxide group ends up, let's see, doing 1 electron attack, making a free radical on the methyl group of the toluene. And then what?
This sulfate group would then be quickly hydrolyzed to a hydroxyl group, forming benzyl alcohol.
Hydroxyl group forming benzyl alcohol. Okay. Okay, and then I think, okay, and then he's saying that you end up having this kind of group remaining here. The 1 lone electron being left on the toluene group. This would then bond with the remaining sulfate radical that's left behind here in the persulfate group. After the other one goes off and has fun. Because, yeah, I guess it's also worth pointing out that, like, this pairing up here would end up being something like HO3S minus, the minus in one of those oxygen. So we got radical oxygen here, sulfate O3 minus. This then pairs up. Forming one of these. And then he's saying rapidly hydrolyzes from the presence of some water, which he explicitly didn't use water. Or, well, no, he did have water, right, from the dissolving this sulfate or persulfate salt. So then with multiple steps, which, yeah, I think are on screen right now from numbers 5 through 7. So I'm not going to draw all of those, just for the sake of time. This would then turn into okay. So then you would have benzyl alcohol, right? All right. That's kind of making sense. And then if we end up having some further oxidation of this, like basically repeat the same thing with another one of these hydrogens bumping off into, another one of these molecules, say, then, yeah, then that could definitely reform, and that could definitely form our benzaldehyde. Okay, that's plausible. Of course, the The issue with drawing this as a mechanism and leaving it here is then it, unanswered question is, why the metals? Because if you remember, this reaction he has both copper 2 and iron 2 salts in here. This entire mechanism that's proposed doesn't actually address what the metals are doing. Copper just being to increase yield, but so we maybe don't have to include that in the main scheme, but definitely if iron is required for this reaction, it doesn't explain what the iron is actually doing in this reaction. And it has to be the iron too, because he did also mention as well that the other salts of iron would work. It doesn't have to be iron sulfate itself. So yeah, that's it's a little bit confusing there. Maybe I could see the iron being, because iron could still oxidize up to iron 3. It's a fairly common oxidation state. Maybe the iron helps this peroxide group in the persulfate break apart, kind of acts as an intermediary, and then makes that more easily accessible by these hydrogen groups on the toluene. Maybe it acts as kind of a docking station for all of this to happen, where you have this CH bond and this OO bond that kind of breaks apart over the iron, and you end up kind of getting like maybe some kind of intermediate complex that kind of looks maybe like this, with like the maybe something that looks like this is what's forming. And then you kind of get to do the shuffle and bond things together and get the state going, but that's highly speculative. I have no clue exactly, but iron does something. This reaction doesn't really say what it does, but it does something in addition to what's written here.
Now, while I am fairly confident that this is the first step of the oxidation, I really don't have any idea how the second step goes. Let me know in the comments if you do know how this would work, but most of the time the oxidation of hydroxyl oxygens to carbonyl oxygens are just glorified E2 reactions where the oxidizer replaces the OH bond with an OLG bond where the LG is a good leaving group. I don't really see how the peroxodisulfate radical could do this alone, so I'm assuming this is where the iron catalyst comes in. Yeah, since maybe. At this point I'm starting to get bogged down on the mechanism while writing the script, let's look at this a different way. If you calculate the oxidation state of toluene's methyl carbon, you can see that it's in its least oxidized electron-rich -3 state. Looking now at persulfate, you can see that the two peroxide oxygens are in the -1 state. Since oxygen is most stable in its -2 state, this whole thing is begging for more electrons, which it'll steal from the methyl carbon. This will result in two stable sulfur.
It is a very, very rough back-of-the-envelope idea of why this could be possible, but there are plenty of examples of like, well, this is a strong oxidizer, and this is a highly reduced carbon, but just mixing them isn't going to do anything together, so.
Sulfate molecules and benzyl alcohol, where the methyl carbon is now in the -1 state. When this happens again with the second persulfate, the methyl carbon is now in the +1 state, resulting in benzaldehyde. A third oxidation would put this carbon in the +3 state and create benzoic acid, which can be easily afforded by oxidation with permanganate or chromium trioxide. This is why 2 equivalents of persulfate are required for each equivalent of toluene, as using molar equivalents would simply produce benzyl alcohol. On that note though, this procedure could definitely be modified as an easy way to produce benzyl alcohol, and if you happen to already have benzyl alcohol, it could be used as a starting point here rather than the toluene. This would require half as much persulfate, and you could probably eliminate the ethanol altogether if you went this route. Anyway, with my best attempt at the theory out of the way, let's look back at the reaction here. As you can see here, the mixture did darken somewhat as the reaction went on. I'm not really sure whether this is a feature of the reaction or a result of my very inconsistent temperature control. I did find that the ideal temperature for this reaction is right around 70 degrees Celsius, and heating closer to 80 degrees Celsius caused the ethanol to start rapidly boiling away, along with the formation of this brown polymerized crap that stuck to the sides of the glass. You'll also notice here that at a certain point, I completely removed the boiling flask from my hot plate and transferred it to a stir plate. The reason I did this is because once around half of the persulfate had been added, the reaction became a lot more obviously exothermic, and this is why I accidentally let the temperature go too high a few times. However, this does have a benefit because at this point, it's not really necessary to apply heat to the flask at all, as the heat created by the reaction itself easily maintains the temperature at 70 degrees Celsius.
As I'd mentioned
anyway,
earlier.
Once all of the persulfate solution was added, I allowed the mixture to continue reacting for another 15 minutes before I cut the stirring and allowed it to cool. I then transferred all of this to a 1-liter separatory funnel, at which point I was hit by an overwhelming cherry smell. This was pleasant at first, but I promise you it got really old really fast.
From the Baja Blast.
Anyway, I next drained away the lower aqueous layer, set it aside, and then collected the upper organic layer containing my benzaldehyde. I then rinsed my reaction flask with ethyl acetate to remove any residual benzaldehyde, and then added this to the separatory funnel along with my earlier aqueous layer. This was then rinsed 2 more times thoroughly with 50 milliliter portions of ethyl acetate to extract all the residual benzaldehyde, with the organic...
I guess it's worth explaining a basic extraction, but what he's doing is that since he had a water layer from all the water he added for the salts, and an organic layer from the fact that benzaldehyde is an organic molecule, it's more soluble in organic solvents, and so he had like the a couple of those in the reaction flask. Or well, it's less that he didn't actually have. Okay, he had ethanol or methanol, whichever it was at this point, but that fully mixes with water. What he's doing is trying to drag the benzaldehyde out of the water it doesn't want to be in by washing the whole solution with an organic solvent, ethyl acetate, to pull it out of the water and just make a big combined dark red kind of gross organic layer, from which he can then do other things to purify. And you want to do this just so that way you can get all the water out of your way, because there's a lot of water, and if you just want to work with less material, it's just more convenient from a practical standpoint.
Organic layers being combined with the original extract each time. I then returned the combined organic extracts to the separatory funnel and rinsed them once with distilled water and twice with saturated sodium chloride.
Now I know we just said we wanted to get water out of this, and it's true, but the point of adding the fresh distilled water there is that if you notice, our original aqueous layer is very green, and that's from all the iron salt still left over it. That thing is probably saturated with salts, and as a result, the organic layer, even though it doesn't really like salt, still probably has some in it. So if you wash out those salts with water, then you can just discard that with your aqueous waste. And again, it'll make purifying your organic compounds easier if you don't have salts mucking everything up.
At this point, I was left with a wet mixture of benzaldehyde, unreacted toluene, benzyl alcohol, ethyl acetate, and some unknown reaction byproducts. I decided first to add a few grams of anhydrous magnesium sulfate to the mixture to pull out any residual water, and my plan from here was to try and purify my crude benzaldehyde by distillation. To this end, once I felt the magnesium sulfate had enough time to pull out all the water, I went ahead and filtered the mixture directly into a boiling flask. I then set it up for a short path distillation and began distilling the mixture. Crystal. My idea here was that the ethyl acetate should distill off first around 77°C, and then only once all of it had boiled away, the temperature would spike to 110°C where the unreacted toluene would distill off. This would be followed by a second spike to 178°C, at which point pure benzaldehyde would begin distilling. However, what really happened is that while the initial distillate was indeed nearly pure ethyl acetate, the temperature of the distillate didn't hold at the boiling point of ethyl acetate. Instead, it slowly crept up to a point somewhere between the boiling points of ethyl acetate and benzaldehyde, where it became clear that I was distilling a mixture of benzaldehyde, ethyl acetate, and probably unreacted toluene.
Well, at the very least, you leave all the red crap behind, but Yeah, I get that's a important thing to point out, and I think I've mentioned this in some previous videos too. But what's happening is that he's getting what's known as an azeotrope, which let me spell that out for you. An azeotrope is basically a mixture of liquids that, due to the mechanics of entropy and enthalpy, the mixture is more stable together, apes together strong kind of deal, where even if you have different components, like he does, like the ethyl acetate, that's very poorly drawn. So let's see, ethyl acetate, the toluene, and the benzaldehyde. You have different boiling points for these. I don't remember exactly what he just said they were, so I'm just going to kind of estimate from my memory of what their boiling points are. Something like 80 C, and then this is something like 105. Even though these have individual boiling points and would boil at these temperatures as pure compounds, if you have them together, azeotrope. You get a new BP that is typically somewhere in the middle of all of these. And all three of them are going to distill over. Let's just kind of round this to be like, 85C or something like that. Doesn't always have to be exactly that way, but it happens because the molecules, they like to stick together. They, in fact, like to stick together more than they like to stick to just themselves. And, again, there are various entropic and enthalpic reasons for this, but you can kind of see why these molecules maybe like to pair together. I mean, the ethyl acetate, the acetate group here kind of gets nice pairing with the aldehyde group of the benzaldehyde, so those two kind of have a positive interaction together. Toluene and benzaldehyde both have aryl rings, and those rings like to stack on top of each other, and so having some variety in said stacks within solution is actually quite nice for an energetics purpose. And the ethyl acetate and toluene don't really have all that much in common, but the benzaldehyde kind of acts as a glue for these two abundant solvents to, want to stick around and mingle for a little bit longer. So, yeah, you do end up having an azeotrope sometimes ruins your chances at a distillation. But, well, it seems that he seemed to have combined everything back into the red mixture, but I mean, honestly, I would have started, I would have taken the idea of, oh, well, shit, at least I got this separated from, like, all the ethyl acetate. At least I got this narrowed down to 3 things in my short path distillate. Then I wouldn't have to worry about all this red crap that's left over, because all of these molecules are clear. It would have just been a manner of trying to figure out how to get rid of the other solvents, which, maybe if distillation itself wouldn't work, you could try just evaporation. Benzaldehyde's fairly, it's somewhat volatile, meaning it wants to evaporate, given that you can smell the cherry smell, but it's probably less volatile than the others. But hey, he does more practical chemistry than I do, so let's see what he's got up his sleeve.
With that said, I think something with a lower boiling point like diethyl ether would have been a better extraction solvent than ethyl acetate, but sadly, I'd used up most of my ether a week earlier on a different project. At this point, I feel like I probably should have just continued the distillation to remove all of the brown discoloration, but in my moment of panic that things weren't going like I expected them to, I instead cut the heat and pivoted to an entirely different workup. For my backup plan, I began by mixing up a saturated solution of sodium bisulfate by adding sodium metabisulfite to around 200 milliliters of water until no more would dissolve. I then began to slowly add my crude benzaldehyde, which quickly caused the mixture to become somewhat cloudy. What was happening here is that aldehydes will form an adduct with sulfite, and the benzaldehyde sulfite adduct in particular is insoluble in the presence of excess sulfite as well.
Sorry, I know he's explaining it right on screen, but I guess I'm in a drawing mood tonight. Yeah, basically you're getting this bisulfite ion. It wants to bind in through that very vulnerable group through multiple steps. You end up getting something that looks along the lines of this. Right. Oh, well, he's kind of... This looks like there's multiple of the same going on here. Oh, no, it's just like what pH you get based on how much you've deprotonated the... How much you've deprotonated the bisulfate. Okay. Let's reimagine for a second. This still has its hydrogen there, so that way I can just more easily kind of draw something like this then. Yeah. So then the easy thing is that if you just then add so this will be soluble in your organic solution. So you have the metabisulfate interacts with your benzaldehyde in the mixture, exclusively the benzaldehyde in the mixture. Then you just add some base. Then you'll be able to... you'll get these as negative charges, and this is water soluble. Oh, this is organic soluble. Which is then fairly easy to separate out, all things considered, because you're... if he's mostly just trying to get away from all the rest of the organic crap, this is a great way to just put this back into water again. And then once it's back into water, you can just hit it with acid to make it go backwards. And it will redissolve in organic stuff. But I'm also pretty sure that acid goes further and kind of recleaves it back off, so then you can go ahead and get your organic product that way. It takes a couple extra steps, a couple more reagents, a lot more time. You might lose some stuff in transfer, but I mean, hey, if this is your option, then this is your option.
Well as in organic solvents. My new idea was to collect this insoluble adduct, rinse it thoroughly of all impurities, and then break it back down to hopefully pure benzaldehyde. To that end, I went ahead and added all of my crude benzaldehyde along with my distillate from the last step, and allowed it to all continue reacting under strong stirring for another 30 minutes. I also added a few extra scoops of sodium metabisulfite to assure that sulfite was present in a large excess. After 30 minutes had passed, I was left with a mostly uniform slurry, and the cherry smell had completely disappeared. I then passed this all through my Buchner funnel to collect the insoluble benzaldehyde adduct, rinsed it thoroughly with both ethanol and acetone, and then transferred the paste to a petri dish to dry. Here you can see the filtrates from the initial filtration as well as the ethanol acetone rinsing. The upper layer in the flask on the right hopefully contains the ethyl acetate along with the unreacted toluene, while the flask on the left should contain all the other water-insoluble impurities in the crude benzaldehyde. Anyway, after a couple days, my benzaldehyde sulfite adduct was now totally dry, and so I went ahead and weighed it for a final mass of right around 60 grams. Allowing it to dry completely like this really wasn't necessary, and if anything, it might have made the next step take a lot longer than it would have otherwise. For this next step, I simply added a saturated mixture of sodium carbonate to a separatory funnel, followed by about half of the benzaldehyde sulfite adduct. This was then aggressively shaken and then allowed to rest briefly before...
So this is basically taking it back. So when, I guess when this was dissolved in water, drying it out will start making some of the hydrogens from the water go back onto here. So that way it ends up basically recrystallizing as this organic soluble stuff. Or if there's any salts remaining in the water from the base, it might also be attracted to something like a sodium ion bound to this oxygen here. And so putting it back in the basic solution isn't going to take this acid pathway and take it back to the benzaldehyde, but it will get us starting from here again, getting everything dissolved, and then we can actually work with that a little more. I'm pretty sure that's what's happening anyways.
We're giving it another good shake. What's happening here is that in the presence of a base, the benzaldehyde sulfite adduct will break apart into benzaldehyde and the respective alkali sulfite.
Well, never mind.
As the reaction proceeds, an
apparently
upper
base
layer
also
of
just does this
benzaldehyde
again
will start
too,
to form along with the return of the overpowering cherry smell. This whole process did take a lot longer than I expected, and I think it would have gone a lot quicker if I had done this while the adduct was still wet. Regardless, after a lot of shaking and the addition of a bit more sodium carbonate, eventually the adduct had been completely broken down and liberated all of the benzaldehyde. I then went ahead and allowed the layers to separate, drained off the lower aqueous layer, and collected my upper benzaldehyde layer in a small flask. I then rinsed the aqueous layer once with most of what little diethyl ether I had left, and combined this organic layer with my benzaldehyde extract. Now at this point I had a flask containing mostly wet benzaldehyde along with a little bit of ether and whatever is responsible for this stubborn orange discoloration. To try and clean this up, I began by drying off the excess water with more anhydrous magnesium sulfate and then removing the wet magnesium sulfate by passing the mixture through
magnesium sulfate is just really good at picking up water without dissolving.
I then added about a gram of activated carbon to the filtrate and shook the flask aggressively to try and remove some of the discoloration. This was again vacuum filtered to remove the carbon, and as you can see, this step did a pretty good job of removing most of the residual discoloration.
Yeah, organic carbon is just good at picking up random tars and shit.
I simply set the flask back up for another short path distillation and quickly boiled away all of the ether. This time there was far better separation of the boiling points, and the moment all of the ether had boiled away, the temperature rapidly spiked to the boiling point of benzaldehyde.
There we go.
Given that benzaldehyde is a fairly delicate molecule, particularly when heated, I decided to cut the distillation here and accept a minor impurity rather than risk destroying the product I'd worked so hard for. As a little indication that maybe skipping the distillation really was a good idea, this receiving flask did catch a few drops of the benzaldehyde before I cut the heat. And as you can see, it quickly began to dimerize to benzoin, which formed long, thin crystals. I'm not really positive why this happened, but I've always had bad luck trying to distill this stuff. As a final cleanup step, I decided to pass the benzaldehyde through a 0.5 micron syringe filter into my final storage bottle to try and remove some of the slight haziness that was present in the flask. At this point, I was now finally done, and so I weighed my nearly pure benzaldehyde for a final mass of 41.83 grams.
That's a bit of a
72.
That's a bit of a half-assed technique alert, which I maybe have been guilty of doing this every once in a while in my when I was an undergrad.
For a final mass.
But what he just did there was the classic blunder of, oh fuck, I forgot to weigh the bottle that I actually added my stuff into. Let me just weigh another bottle that is, of the same make and model in order to zero out the scale. And be like, okay, I'll subtract that out from the mass that I measure here in my full bottle, which gives you a rough estimate of how much you made. However, it does suffer from the fact that no two bottles are exactly identical and weigh the exact same amount. So, you could have a variance of a handful of milligrams between, your measurements, but it's often better than not knowing anything at all. So... or wasting another piece of glassware, especially if you're just doing home chemistry. It doesn't really matter, but...
0.83 grams, representing a 72.7% yield. While I am happy with this yield, it is about 20% lower than the literature maximum for this procedure. I'm almost certain I could increase this number by more careful temperature control during the reaction, as well as simply picking one method to clean up my crude product and then sticking with it. Since I don't really have proper equipment for any real analytical testing, the only method I could think of to confirm that what I've made here is truly benzaldehyde apart from boiling point and the distinct odor is density. Benzaldehyde has a density of right over 1 gram per milliliter, and as you can see here, the density of 25 milliliters is just over 25 grams. Apart from that, another way you can tell this is benzaldehyde is simply by looking at it here in the bottle. Benzaldehyde is strongly refractive, and it causes a slight rainbow effect at the bottom of the bottle that you really won't see with most other liquids. In any case, that's all I have for today. As I mentioned earlier, this video is only the first in a long series of videos I'll be putting out on some of the different things you can do with this incredibly versatile chemical. If you're interested in seeing those, feel free to subscribe. And as always, I want to give a big thank you to all of my members.
Wonderful. Oh, that was a cool little bread and butter presentation there on making benzaldehyde. Fairly accessible too, all things considered. Nothing he mentioned, like, for synthesis was all that expensive. The biggest expense there is just getting the equipment to, do distillations and all that. But all these other salts that he's mentioned are pretty simple. So, I don't know. You want cherry smell, and legally speaking, you don't want to consume it, and you will not be actually, you will not be consuming it in any manner, because liability. Then here's your answer. All right. I kind of actually wanted to not watch Nile Red stuff today, but it is in the title of the video, so I probably should actually get to the Nile Blue. Eventually, oh, don't worry, Dysprosium and Glass to Gold. I'll get to reacting to you one day when I run out of Nile Red stuff to react to, the big title things to put in the video. Alright, so this is Nile Red's alternate channel, Nile Blue. It says he's making Superbeer. I don't know what the hell this is, but this released just about when I was going on break, so I didn't have time to react to it when it was flashy, new, and relevant. However, I'm still interested in whatever the hell this is. I think what I maybe gleaned through context, and maybe, I guess, what the thumbnail is trying to point out here, is that he's probably doing the same thing he did with combining 100 cans of Red Bull into 1 can of Red Bull. So he's trying to make this a 100 times concentration, or whatever times concentration of beer. Of course, thumbnail's a little misleading. If it was 100% alcohol, then it would just be pure ethanol, and he's already made pure ethanol by enzymatic digestion of toilet paper, so you don't need to do it this way. But my guess is it's more of a discussion of, yeah, had 1 can of beer, let's combine like the volume of 100 cans of beer into 1 and just see how absolutely overflowing with hops and other shit is in there. I'm kind of a beer hater myself, honestly, so I think this is probably gonna be more nasty for me than the Red Bull one. But, maybe it'll be interesting here. So, let's give it a go.
This video has been sponsored by Odoo.
Odoo?
This is beer.
Odoo has that fucking vibe of, like, that one meme of, like, you make sure to poke on Snow Scraper. Did you, be sure to send a fax on, Skladao? Gotta be sure to tag your boss over on, Cheese Grater. Did you jizz me on Smack Dog? Don't forget to jizz me on Smack Dog. It's got that same fucking dog shit meaningless 2-syllable naming that you only find in office buildings. Anyways.
And for the most part, people generally think it tastes good.
Wrong.
But in my opinion, it's always had one fatal flaw.
That it's beer.
Which is that it's consistently the weakest drink that you can buy in terms of alcohol content, and it seems to just struggle to even make it past the single digits. Some people claim that this is because of just limitations in the brewing process,
boy just wants to get drunk,
flavor reasons, or even, I guess, laws or something. But personally, I just think that all of these are just lame excuses that are...
it's mostly laws in the sense that if you actually took beer and made the content of beer more alcoholically concentrated, then you're just not making beer anymore by definition. Like, that's where you get shit like brandy and whiskey from. Like, that's where your more concentrated, harder dark liquors are from. It's just concentrated beer. Are you just gonna make beer or like brandy this time around?
Needlessly holding beer back. I think that beer should be able to go up to any percentage that it wants. And at least from some preliminary research, I was actually able to find some people that have already pushed the limit to a respectable 30%.
Yeah.
With a bit more research.
Probably illegal in 15 states based on that article, only on the sheer fact that it's not beer at that point, at least within those states, like, you know, laws.
I was then able to find this abomination, which is apparently at 67.5%, and it's honestly way higher than I ever expected to see a beer.
However,
in my opinion, though, this still isn't nearly enough, and I don't see why it wouldn't be possible to push the limit even more and to go up to 75%, 85%, or even maybe 100%.
Know what 100%
so that is
Niall.
What we're going to be doing today.
100% is pure ethanol.
How strong we can get beer. What is the true limit? But with that being said, I guess we'll just get started. And to do this, we put together this amazing tower of
the beer tower.
Generic beer. We also got exactly 20 of them, because at 5% alcohol each, we should be able to take all of this and crunch it into one can.
Not how math works.
I mean,
not how math works.
I highly doubt you can't have 100. There's probably some limits of physics and other stuff that would prevent that, because I mean, if it's pure alcohol, there's no room for the beer. But I mean, either way, that's
you're doing frat boy math right now rather than chemist math.
Okay, so yeah. To start with the concentration process, we just need a bucket.
The reliable bucket.
That
bucket's smaller than before.
And adding all of these beers into it.
What happened to the big Red Bull bucket?
So, one added successfully. Number two.
Okay. Pouring ASMR.
This is way too familiar to the what we did with the Red Bulls, and I'm not going to make the same mistakes that I did last time.
Sure you won't.
What I'm going to do is I'm going to speed things up immediately, and I'm not going to open them manually. Instead, I'm going to use this beautiful Nile blue bottle opener.
Ooh.
This somehow feels slower than just cracking them all open manually, and more dangerous too. I would stab myself doing that on accident. All that foam. What an amateur pour.
Okay. And that's it.
No kidding.
We now have a bucket of what should be around, I guess at most, like 7 liters of beer. And what we have to do next is remove the foam.
Okay, at least he's not just getting his hands in there.
Also, up until now, I've realized that I kind of never explained anything or even remotely alluded to what we're even doing here.
Yeah, I was wondering that. I was waiting for when you were going to say something.
I don't know. I just completely slipped my mind. But yeah.
I'm just so excited by the idea of drinking 20 beers at once.
I mean, as far as I know, it's basically impossible to brew beer past like 15% or something. The yeast just like will not survive. So the only way to get higher, and from what I've seen from the concentrated beers online, you kind of need to take normal low percent existing beer and use some special techniques to concentrate it.
What are those techniques, though?
I think there's a bunch.
Will it involve the very expensive spin dryer that you bought several months ago?
The 67.5% one, they just repeatedly froze it. And, I mean, the alcohol with the beer flavor just slowly concentrated. But
that's another azeotrope type thing from the last video.
They were really hitting their limit using that technique.
So also applies to freezing points, not just boiling points.
A different technique called freeze drying. With freeze drying, we should be able to push the limit up to nearly 100%.
Okay.
I think we should be able to sail right past 67.5.
All right, so when is this done? I don't think that foam will ever go away.
Oh, that's
no,
nonsense.
I don't think the foam's ever going to go away, but we can get most of the CO2 out, just so it's like actually not fizzy anymore.
If he planned ahead, you see, he would have put it in
that is very flat.
He would have put it in a container that you could actually use. You would put it in a container that you could put a pressure chamber lid on, and then just vacuum out all of the CO2 foam, and then let it just go flat, putting the pressure back to normal.
I don't think we're really going to be doing any better. So I think we're ready to move on to the next step, which is the freeze drying step, where we get to concentrate this and remove all of the water. So we got our
He's using
freeze dryer
the
here,
other expensive piece of equipment from China
brand
he
new.
ordered several months ago.
And it's a significant upgrade to our last one.
Oh yeah, big upgrade.
And we have some, I mean, we didn't get it just to make Superbeer. We have some big ideas for it. But with that being said,
But for its
what I have to do
inaugural
now
run.
is just get all of this beer into there. And in order to make it all fit in there, we need to measure out about 1,200 milliliters at a time. And we'll pull out one of the trays.
Oh boy, so this is going to take a while.
Super long stainless steel
Looking
thing.
at several batches at
And
least.
We just gotta pour the beer onto it. Okay. That's perfect.
Ooh.
Ah, okay,
Perfectly
each one is a
calculated.
1,200
So that's good. We can now slide
milliliter tray.
beer tray 1 in. And we will go for tray 2. Okay. Tray 2.
It's worth mentioning, like, a freeze dryer typically works
tray
by having,
3.
like, heating elements underneath
Tray
all of those
4
plates,
filled.
and then a cold surface on
Tray
the
5
outside drum,
complete.
where, like,
And I'll slide
that like, the
one
whole
in.
chamber is contained within.
That's effectively
And so it's
it.
like, you end up having heat
And
under the
I should
plates,
also say that
drives off
all we're
water,
trying to do
freeze
right
onto the
now
sides,
is just freeze
just
the
gets
beer.
rid of the water.
Oh, okay. Just freeze
Now,
the
if this
beer
is not going to
first.
affect the
Yeah, I
ethanol
wanna
is another
make sure
question.
that it actually freezes properly before the drying process.
Okay.
That it's gonna do. So yeah, we will. We'll come back to it. We'll you know, we just got to give it some time.
Who's not starting the drying part, just the cold part. After 7 hours.
Okay, so we're back. And if we look now, we can see
Lots of
what
condensation.
looks like some extremely frozen beer. Okay.
Holy. Oh,
Pretty
my.
frozen.
And that is our beautiful beer.
Woo.
Looks amazing. Yeah.
Oh, yeah, that's solid.
Confirmed solid. We're good to go. So I think we can put it back in.
Crack open a few. Put some beer
now,
cubes in your water.
Theoretically,
Opposite
everything
of
frozen,
ice cubes in your beer.
yeah, we should be able to just move on to the next step, which is drying it. That's what we came here for,
Yeah.
right?
Still feel like
we
this is
can
just going to
start
cause the
now.
ethanol that's in there to just go away, because that has a
Okay,
lower
so
boiling
starting,
point.
And now,
Yeah.
should be pulling a vacuum. And, oh, look. All the beer is foaming.
Oh my god, yeah, what? Is that the alcohol?
I think that's the alcohol boiling out of the beer.
Okay, so we're
so
losing
he's-
alcohol right now. Like, this alcohol is just, where is it going?
Getting wasted. He's realizing the problem
I mean,
with this
as far
method.
as I know, it's going straight into the vacuum pump.
Hmm. Interesting.
So wait, so, like, I
I
don't
wonder if you
understand.
could have foresaw
How is
this.
this concentrating our beer? Like, what?
Yeah, so I should explain something. So as we mentioned before, this part is the drying process of the overall process called freeze drying. So the first step was we froze the beer, and now by pulling a vacuum, it will dry it and
Of
leave
water
behind
and ethanol.
just the essence of beer.
Beer
Just the
essence.
Pure beer flavor. But it will effectively be alcohol free.
So wait, how exactly is this going to be super beer then?
That's a very good question. And once we actually confirm that we can get dry beer from this, I'll talk more about it. I don't want to jump too far ahead of ourselves right now.
Right,
Okay.
right.
So he's just going to mix pure ethanol with this. to get Superbeer then. He's concentrating the beer in a little bit of a cheater's manner, which, fair enough, but still.
Let me pull it out.
It does feel a little bit like cheating.
Is crispy.
Congratulations, you have basically like hops crystals.
Oh, yeah.
He's cutting it with a knife.
Look at that.
Fresh crystal.
That's some...
Whoa.
It's gonna move some of this
That's
out.
some dry beer.
Go get Jesse Pinkman on the scene.
Oh my gosh.
I mean, that's it, but I guess I gotta try some of it, right?
Yeah, definitely.
Try a little flake.
Snort it. Snort it, Nigel. Snort
This
it.
thing here.
You know you want to. Like, wow, that's terrible.
Holy.
It's terrible, just
That's
like
the
beer.
strongest beer you can possibly have. Just straight up pure beer flavor. My God. That was powerful. But I guess with that being said, the first step to turning this into our hopefully amazing super beer is to first get all of this powder off of the trays. We'll just start scraping. Okay, so
Right.
that's good.
It was very funny seeing
I'll
him
just start combining
with
all
one of the trays kind of holding it in a different orientation. The spatula is just kind of like, all right, I forgot this man never uses kitchen utensils. This is the hardest part of the things for him.
Okay.
It does
Yeah,
look very pretty,
about
though. It looks like
We
gold
now have
flakes.
A tray of 20 powdered beers. And all we have to do now is turn it into one super beer. And up until now, I've only vaguely talked about how we're going to do that. But the process is really simple. Basically, we just need this.
Pure
100% ethanol.
Oh my gosh.
And it's also kosher, halal, and
Very
USP
accessible at home.
/FCC. So it's fully food grade. And the idea that I had was that I would basically just mix the powdered beer into the ethanol, and that would be it. Until I kind of realized how much solid stuff was actually in beer, which kind of shocked me. I mean, just as an example, look, that does not look promising for volume, but this powder is super fluffy. So, who knows?
He's just gonna hope that he gets the volume he needs,
Maybe
and
some
that
sort
all
of
this is
miracle
just
will happen,
super soluble in
and
ethanol.
It all melts into a volume that'll fit into a single can. But I guess we will see.
It's not impossible, but
I mean, I think that to me, there's only one way to
quite
find out.
think it's gonna work the way you think it goes. There is 30 minutes of runtime to this video, after all.
Looks like sawdust, honestly.
Okay. So we'll open this up. Crack open our pure ethanol.
I think the funniest
wanna
possible
try it
result
first, though. You
is
gotta-
if
you
he
gotta get
ends up
baseline
running out of
of
ethanol and he still doesn't dissolve everything. Then he has to order another one. Yeah, it's like eating an organic solvent because you basically are doing
Some
that.
high purity stuff. There's literally no flavor in it.
Just happens to be one that won't kill
Okay,
you immediately.
So, I think we have a leeway of about 130-ish grams. If we add that, it'll still fit in the can. Okay, let's wet this beer. Oh.
Well,
Now he's gonna play with it.
Well, yeah, I mean, it wetted pretty decently, but 24 grams and it vanished. It soaked it up like a sponge.
Yep. So there's gonna be a lot more doing to get this done, it seems.
Uh-oh.
yeah.
This is hopeless.
Let's just try it. Let's just stir it around a bit. Yeah, that's not. You have so much. We have so much more to go.
Yeah, this is one of those projects that really, I don't know how I even thought this was ever going to turn out.
I don't think he did. Time to get the industrial truckloads of ethanol. That, I will say, that is actually shocking how much it is absorbing. It's like oatmeal in water.
It's so thick.
Okay, well, how do you feel about the idea of Superbeer being a powder?
It doesn't hit the same thirst quench that you get from a beer, you know?
You're right. But, well, I guess, you know, at the very least, I will taste it. You know, you can't bash it until you try it.
I'm sure adding water would actually help all these things dissolve. They were probably more water soluble than they were ethanol soluble, given why beer is mostly water, but that would betray the idea. Oh, it's horrible? Really? Yeah.
Holy. I've never had an experience like that in my life. It tasted like eating sand a bit, but then it all melted, and then it tasted horrible, but then it tasted okay, and then it burnt again. Oh my god. No, this is, I cannot rightfully accept this as Superbeer.
This is an I regret everything kind of moment.
I think this was an interesting experience. But I think we do need to move on forward and push forward. We still need to achieve our goal of Superbeer. Just now, it's a little bit different than we first imagined. I don't know why. Before, the idea was to get all the flavor plus the alcohol. But even in hindsight, that doesn't make too much sense. I think you want the normal flavor of one beer, but the percentage is higher.
Okay.
Yeah. You don't want the flavor and the percentage.
Right. And how high are we getting the percentage at? Like 100, right?
Yeah, I think that's the goal.
He basically just wants to take
for 100%.
All right.
We're just pivoting away from the idea of including all of the flavor of 20 beers in that 100%.
Okay, yeah, that makes sense.
So yeah. It's going to take the much more manageable task of just one beer's worth of all this yellow powder. So he's probably going to freeze dry another beer. And then just dissolve all that in whatever the volume of ethanol would fit in that can. Okay, I guess. It feels like a bit of a betraying of the word of super beer because you're emphasizing the beer part of that. But I get why this is the practical route. Maybe call it just stronger beer, not super beer.
Flavor do you need to add in order for it to actually taste like a beer now?
Well, I mean, it's kind of like simple. We just need a 20th of this. Yeah, we just divide whatever we have here by 20 and put that into some 100% ethanol. Okay, so 24.9 grams is one beer. Oh, 24.9.
Well, that doesn't account for the fact of all the ethanol that's been absorbed into that.
One full beer. And
again, I can't blame him for not wanting to freeze dry another can over the course of a day.
What happens? But it would be unacceptable to just add the ethanol without carbonation. So to get around that problem, we've got a soda stream.
Could you even carbonate ethanol?
I have my strong suspicion that it does not work. But we have to at least try.
Right.
Yeah, because carbonic acid dissolves in water a lot better, but I mean, I don't know. It's still organic. Maybe you can get it to work. I mean,
it doesn't look like it's doing anything, guys.
We'll see. Now, darn.
Yeah, I mean, it's kind of expected, but at least we tried. Now, we have to just add it to the cup, and we'll see what happens.
Well,
will any of this powder dissolve?
Superbeer V2 is about to be a very flat experience.
I mean, it's doing more than I thought it would. Like, it's becoming murky. It's all just sitting at the bottom still, though.
Yeah.
Here, I'll just stir it.
Tiny whisk.
Oh, man.
No.
No? Yeah.
So, here's the thing. It's like virtually colorless.
It looked like it picked up nothing.
Yeah. Like, I'll try it. I'll see.
Yeah. Again, it seems like most of the beer solids are water soluble, not ethanol soluble.
No, that's effectively just ethanol. So it actually literally, I think as far as I can tell, at least in terms of like flavor, dissolves nothing.
Whoa. So,
I mean, we have to add water. Like water is absolutely necessary to dissolve it.
Wow.
Yeah, so this is getting a little bit complicated.
So you have to add water, which will drop our alcohol percentage.
So now we'll see if we can't get to like,
That's
you know,
fine, right?
maybe a 90 proof or
what are we dropping the percentage
180
down
proof
to?
or something.
So
if we add just like a little bit, right?
Yeah, so like I don't know. It's gonna have to be calculated as we go.
Okay.
And I'll just write down the current alcohol amount, 138.3. And now for the water, we can actually get it fizzy. So in a way, this is good.
Okay.
You know, we're actually gonna.
You know,
have it
plus
fizzy
maybe the
because
acidity of the
I guess
carbonation will
Superbeer
help
should-
too with the dissolution of things. A low pH
And
might be nice.
It should actually work this time. Oh yeah, actually.
Did not work. Lamau.
Oh yeah. That actually worked.
All right. Well, now we got to try.
Now you gotta try doing the
one more
ethanol
time.
again.
Yeah, that's fair. Because, like, it kind of got completely scammed. So I think we'll just add the rest. Okay. I'm ready to be surprised.
Still doubt it would work that well, but yeah, maybe.
Okay.
No,
Ooh.
that looks entirely
Huh.
flat.
I think CO2 does dissolve into it, but I don't think it's getting carbonated per se. I think it's just, like, has CO2 in it. I mean, we'll see. Oh, I poured it on the spoon, and look, bubbles came out.
Yeah, it doesn't exactly
gosh.
show
I think it does work.
well against a white background. Oh, okay, it definitely works.
That's fizzy that's crazy fizzy. Oh my god. Well, there's also the burn of the ethanol, but that totally works. And with that revelation, I think we gotta completely abandon this initial attempt. And yeah, we'll scoop another 24.9 in there. Okay, 24.9. Good. And now we're gonna add the fizzy ethanol.
This is still the thing I do like about Nile Red's channel.
Whoa.
Just the fact that he has access to do this kind of stupid shit nobody else would.
That's an unbelievable amount of fizz.
That's awesome. What?
Huh. How about that? Proved my expectations a little bit wrong.
Okay.
That's fine. Yeah.
And now we have to add water. So we're trying to add a minimal amount just to dissolve all of the powder.
That looks like more of it's not dissolving at that point, which is weird.
Oh, it's like coagulating.
Huh. Well, that's the opposite of the result you wanted.
Oh no! Oh my god, it's just turning into like this weird goo.
Yeah.
Well,
Look at that goo.
that didn't... Well, I don't know. Sometimes when you get stuff like that, you just gotta keep stirring it.
I think
Till your
adding
hands
the
are
ethanol
sore.
first is a mistake.
Yeah.
God, I did not know that this was going to be such a scientific endeavor.
This is gonna be it.
Like you're a science
Okay.
channel or something.
So add the water first, and we'll see how it dissolves. I'll add a minimal amount. Oh, look at that. See how much better it dissolves in that? Who could have known that?
Huh.
Stir it. Okay, so it is dissolving.
It is so weird how the order mattered
good.
that much.
Look at the
I guess the ethanol
syrupiness
just kind of formed almost like a protective coating over the...
Okay, so that's like
solid, didn't want to
basically
dissolve.
fully dissolved. And now we just got to add some ethanol to it. But I do think it's going to immediately
once you have only
cause
minimal
stuff to
water,
come out.
you know. Wow, look at that. Right out of solution. Immediately.
Oh yeah, you're right.
Yeah,
like
immediately
a
started.
boiled
oh,
egg.
but it kind of went back in a little bit. Oh. Okay. So let's add a couple more grams. Now we'll stir it. And There's only one part of it that seems to be coming out. Whatever this like white goo.
It's kind of like tempering an egg, honestly.
But it's like breaking
add
up
it
as
in
I do
slowly with a lot of stirring.
It doesn't seem as bad.
It'll actually probably all dissolve eventually. Although you definitely got to have a balance of water in there.
Perfect.
Otherwise, it's just going to effectively be all ethanol, and it's not going to dissolve.
Oh, it's like...
Ooh, it really thickened up there.
Whatever this is does not like the ethanol.
Oops.
Oh, no!
Formed a little homunculus in your glass
again. Do we
again.
have water to go back?
You have to add water.
Happens to the best of us.
And now it's reverting back.
The only problem is that this giant gummy thing is gonna give us some issues.
It looks like someone's chewed piece of gum.
That looks like gluten.
Dude, you should try that.
No.
You should try that.
You want me to?
Dude, what even
I mean,
that?
what's the worst that could happen? It's just from beer.
Whoa. Oh. It doesn't really taste like anything, to be honest. It tastes like some old, flavorless gum that dissolves in your mouth.
Huh.
What the hell is that? That was like not even. It's not even revolting because it didn't taste like anything. I do think that if we add more ethanol, it's going to actually start knocking the flavor out. Because I think the key is maintaining the color. Because the moment the color is gone, we don't got anything. So I'm actually going to add a bit more water, just a bit.
Hell yeah, you gotta have it dissolve.
Okay, so yeah, like I said, I think the game is, as long as it's clear, we're okay. The moment it starts getting like a little bit too cloudy, we have to add the water back.
Right.
But this is the color of a beer. So I think we're on the right track.
Yeah, very light
Start
beer.
adding our beautiful ethanol again. I think this is okay. Like having it a little murky.
Uh-oh. You got a little brown ball at the bottom there.
Okay. So I think we got to do a water again. Now.
Yeah, we got to do one more water for sure. Ooh.
Oh yeah, look at how much it clears up. Okay. And now we will attempt to get up to the 350 mark with pure ethanol. I don't think that's going to happen.
So far, so good. Keep going. Dude, we're doing all right. Stir it, stir it.
I see what they mean by literally just ignoring whatever gunk ball is at the bottom. But that feels like cheating. Like, that's a part of the beer. You're just not drinking that anymore.
We did it.
It's probably like the hoppiness.
So this now should have the flavor of one full beer. And no one knows what this goo at the bottom is. But we just leave that there. That's like a bonus if you make it.
Yeah, it's like the cherry.
I'm so excited. I really want to taste it. But I think before I do that, I have to know what percent it is. And originally I was saying that I have to do all these calculations, but I don't have to, I don't think. Instead, I have this special little thing.
Remember, a little alcohol measurement
that we should
device.
be able to just put a couple drops on it, and it will tell us what percent it is.
Well, if he's going by refraction, the issue is just having all these impurities in there. It's probably not going to be the best tell of how much alcohol's in there.
I'm hoping to beat that commercially available one. If it was 70 plus, I will.
The only other option would be like a little density floating kind of measurement, which would also be thrown off by the object in there.
It's 80%.
No way.
Look,
no
can you look
way.
in there? I mean, at least it claims it's 80% ethanol.
Oh my gosh.
It was
dude,
maxed out and
80%
completely
is
inaccurate.
Maxed out.
Yeah.
It's maxed out. All right.
Hold on. I lost my mouse. I wanted to read
That's
that.
better than I could have
Where is
ever
my mouse?
expected. 80%.
How is it?
So it has the
Oh,
power
uh-oh. My pointer's
of,
doing weird
what
things.
is that, 16
There we go.
beers?
Maxed out, completely inaccurate because this meter is apparently meant for much more pure liquors. Don't you mean... We did the math, though, and just by coincidence, it was actually about 80%. You don't The much more pure liquors, I mean, it has a maximum. I don't think much more pure, unless you're just talking about like something that's, you know, I have no idea what syntax he's trying to put there. That grammar doesn't quite make sense. But hey, you know, coincidence by math, around 80%.
Dude, what?
Cool.
So it has the power of, what is that, 16 beers? 16 beers in one.
Something like that, yeah, what?
And it's actually still fizzy. It's
well,
fizzy.
yeah, with all that carbonation.
That's beer. You know, no one can tell me that's not beer. Actually, a lot of people could tell me that. But also, I feel like I should probably actually taste it and instead of just hyping it up constantly. I think we got to take...
probably awful, because that ethanol flavor is going to dominate the actual flavor of beer.
That's like crazy good.
Crazy good.
Or I hate alcohol, but this is more enjoyable than some 5% drinks.
He's coping.
The burn's not even that bad. Like,
He's coping.
Tell it's ridiculously high alcohol.
He just wants his super
but
beer to be
really
good.
Not bad.
That's awesome.
I'm very hyped on this beer. It has good flavor. You want to try some?
Yeah.
Okay.
But I want like a good amount because I want to get a good flavor profile.
Let's get a shot of it.
Go to the 5 mark.
Okay. Oh, that's
perfect.
All right, let me try this.
Okay, here.
Does not go down easy.
That burns, but that's pretty good. I do taste the beer, but not that much. Honestly, I feel like the ethanol kind of goes over the beer a little bit. Like there's more ethanol than beer, but there is an aftertaste of beer.
I feel like I tasted the beer up front.
Really?
Yeah.
I taste the ethanol a little bit more. Like it burned. It burned at the moment I took that shot.
80% is ridiculous.
Yeah,
That's true.
ethanol burns me
But no,
really
I do
badly.
taste the
Like
beer.
I would
think it's really
taste
good.
that more than
I
anything
think the
else.
combination of the flavors work very well together. It's a good drink, but it hits hard. It hits hard. I think we're onto something here.
Okay, so I mean, I think this is a success.
Yeah, I mean that is definitely super 80% beer, dude. It's unheard of.
All the flavor of one beer, but the power of 16.
Yeah.
Like I said, my target was 20, but I'll settle on 16. That's actually still absurdly high.
Huh.
And you know, and I should say that I accept this as beer, even if other people don't, and also the government.
And now it's time to serve it at the price of all the raw materials you needed to make it. So that'll be about $75 a glass. That's a good deal, right? Oh, and don't forget about the 50% tip that I'm gonna need for pouring that out for you.
Legally classifies it as a liquor. I don't care. But yeah, that's about it. I guess all we can do now is enjoy our amazing creation and bottoms up. It's been a few weeks now, and we've still been occasionally enjoying our amazing creation.
Enjoying Grimace's face.
Except, at the same time, I've been also thinking about the fact that there's absolutely nothing stopping anyone who sees this video from stealing the idea and the name Superbeer and selling it as their own product.
So, he decided to do a limited
And while we
run
don't
under a
currently have
trademark.
any plans of selling it ourselves, I would still really like to hold onto that possibility for the future and to somehow protect the name Superbeer. And full disclosure, I don't really know anything about trademarks, but I feel like the best way to fully lock in our creation is to preemptively launch a Superbeer product website. The only tricky part is that I also don't know
Apparently my
anything
little
about making a
TM joke is
website,
not a joke.
except thankfully we have the sponsor of this
No.
video,
No.
to help us out
Okay,
with that.
it's fine. Have fun. Have fun making your trademark there, Niall. I'm good. I don't need to hear about Odoo. I don't need to be pounded on Odoo. All right. Well, let's see. It is currently almost 2 hours into stream. I could watch one more video. What do I have here? Something that's 20 minutes, something that's like 25 minutes. It's kind of a slow night. That's okay. You know, I kind of feel like heading off anyways. I'm a little tired, so. Yeah, I mean, those are 2 videos today. We had Superbeer from Nile Red, and we had benzaldehyde from apoptosis. So, if you're out there lurking, thanks for joining and watching some chemistry with me. I kind of mentioned in my stream announcement that, you know, I have a lot of these now in my in a playlist to react to later. So, I think I can probably make this a fairly regular series now on the channel instead of just kind of like haphazard every few months or so. I could probably do this. My aim is to do this monthly for 2026. So hopefully I'll see you next month then for some more chemistry react videos. If you're out there in the background, be sure to like the video, leave comments, subscribe, and share with other people. It helps the channel grow and it helps my ego feel good. If you want to join a Discord to talk about chemistry, but also mostly Mega Man and other video games, that's there too. Otherwise, I'll be back next week with some Make a Good Mega Man level 1 on Monday, and some more Doom Plutonia on Tuesday. So with that, I'll bid you adieu. I'm sorry, adieu. And I'll talk to y'all later. Have a good night.